business of today is to talk about our speaker, Scripps geophysicist Donna Blackman. Donna does the kind of research most of you who have visited the aquarium and the museum at all know about, which has to do with the places in the Earth's surface where plates begin to separate. And as these geologic plates separate, the magma comes up to the surface and forms these ridges, and that's the kind of thing that Donna studies. Donna does this work by using a variety of techniques that include sonar imaging and also analysis of seismic waves as these move through the crust to try to get an idea of what the structure's like as well as what the rocks are like. And one of the things that Donna has good fortune being able to do is to actually go to sea and to go into a deep submersible and go down and actually look at these sites. And that's what Donna will talk about today, about her research in describing this area. So gravity measurements, direct observations on deep submersible Alvin, that's what she did last December. So I would like to introduce Donna. Donna got her bachelor's degree at UC Santa Cruz, master's degree at MIT, PhD at Brown University, came to the Scripps faculty in about 1995 as a postdoc, and then has been here now as associate research geophysicist. Donna's title is Exploring an Undersea Mountain, Tectonic Plate Spreading, and Hydrothermal Vents of the Mid-Atlantic Ridge. Donna.
Well, good morning. It's a pleasure to be here. I appreciate the opportunity to kind of pass along some of the aspects of what we're doing. I am going to be presenting mainly a geological perspective today. The work that I'm talking about is work that I've done in conjunction with two other co-investigators, Jeff Carson from Duke University. He's a structural geologist, does a lot more of geologic field mapping, whereas I'm more of a geophysicist. And Debbie Kelly, who's a geochemist, she studies the hydrothermal systems and has been key in our new finding at the Lost City. As Jeff said, I work in the area of the oceans where new plates form, the older plates pull apart, new material comes up from deep in the mantle. And one of the things I want to emphasize today is that we've had the opportunity at this site in the Atlantic that I've been working to look at interaction between not just the crust of the ocean, but in fact the layer that normally resides deeper, the mantle. And there are a different kind of rock there, and in fact the biology and the chemistry of the hydrothermal system is rather different. And so that's the perspective I want to put across here, that we have some sites on the seafloor where the deeper layers of the Earth interact with the ocean and in fact with the biosphere. So that's the unique thing of this site. So what we have is exchange between this deeper layer. The normal process in a typical oceanic spreading would be to have young ocean crust faulting as it's being stretched and pulled apart. Often then those faults will be symmetric and steep. They pull apart, magma intrudes. The faults are the pathways to allow the seawater down in and to have the interaction between the crust and the ocean. So typically, in this normal system of oceanic spreading, we have the steep symmetric faults. Just the vagaries of how this happens. It's not a perfectly continuous process. You have faults, they spread. That develops low abyssal hills, and those are rafted off axis through time. But what I'm going to be talking about today is a different sort of episode that occurs every now and then, and that's when instead of steep symmetric faults, we have low angle faults, and they're asymmetric. They're not even about the spreading center. And that ends up bringing up a whole new side of geologic processes, and in fact in the long run a different type of hydrothermal system and a different type of biotic system. So here we are looking at the seafloor. We're in the Atlantic. Let's see if I can point to it. Yeah, so here's the east coast of North America. Here's Africa. And if you can just make out the line coming down here, this is the Mid-Atlantic Ridge. It's the line where the plates spread apart. It's the plate boundary. The box here is the study area. And here we are looking in detail at the blues, which indicate the deeper part of the Rift Valley, coming down here. But what you notice, and this is typical in the Atlantic, is that rather than being a single line, the rift often is offset. And here we have a transform fault. This is the type of fault where the two plates move sideways in a horizontal sense, just like the San Andreas does. And that offsets the system of spreading. And it turns out in this case, that's a key part of this story, we believe. We're still trying to understand these structures. So we're going to be focusing in on an area right here near the intersection of the Mid-Atlantic Ridge and the Atlantis Transform Fault. So we'll zoom in now. So here we are seeing that exposed in a higher resolution. And here's the Rift Valley. This is the Atlantis Massif. This is what I'll be focusing on here. And you can see the indication with the red is that this is quite shallow. It actually gets to a depth of 700 meters compared to 5,000 meters depth at the Ridge Transform intersection. This is a lot of relief. Even on land, this would be a quite steep mountain. Okay, what I want to point out here is that we have this feature, an oceanic core complex that we're working on. But in fact, here I'm going to point out the episodicity that I referred to earlier. This system has formed over about the last 2 million years. But you see, most typically are the abyssal hills I referred to earlier. These are the low relief, linear spreading system parallel features. That's the typical thing. But we can see that here, formed at this part of the spreading system, is another one of these core complexes that formed probably 3 or 4 million years ago and has been rafted off axis. Another one of these systems is shown here that formed about 10 million years ago and has rafted quite a bit further off axis. So that's sort of the sense. You can see that, oh, there's sort of every many million years, this type of episodic low-angle faulting seems to go on. And we see this in other areas around the Atlantic and in the Indian Ocean, in the Arctic Ocean. And that's why we think that this is important, because we have these opportunities to expose lower crustal, upper mantle rocks when we have these episodes of low-angle faulting. Now, here I am talking as if we fully understand these things. Well, in fact, there's a lot of questions about it, and this is what I'm going to try and get across, is how we go about obtaining information about these systems, how we try and get to them. What I've been showing you is just the shape of the seafloor. And in fact, that was our first piece of information, was just the fact that this was shallow and the fact that it has certain, a block of material that's deeper and off to the side, and it has kind of corrugations on the top. We'll look at these in more detail. So we can use the shape as a first piece of information, but until we start collecting rocks, until we really get down there on the seafloor, we're having to use some other remote instruments to try and understand what's going on. Okay, let me just first show you our cartoon, try and help you visualize the processes that I'm talking about here in the faulting and the contrast. Here in the top, I'm indicating the typical symmetric steep faults that occur. Here you can picture a block before it's been pulled apart, then you apply these horizontal forces and you get the steep faults, and the median valley drops down, and there may be offsets in the rift system. Now, of course, this is a picture taken from on land. In the oceans, we'll have magma coming up here to supply the new plate. The difference in the systems, these episodic low-angle systems, is that if you have the center of rifting over here, the faults are lower angle, they dip off to one side, and in fact, what you end up is the material that used to sit next to this part of the system tilts over like domino blocks and gets rolled over. When this goes on for on the order of 1 million years, you actually end up getting areas that are deeper and then areas that are quite shallow because of flexure in the plate. The plate has some rigidity, and as you apply the forces, it actually will bend, and in fact, part of the bending is an upbending. So that helps to produce the topography. One of the things that's exciting about this type of geologic process that we see in the ocean is that it's very analogous to something that we can study in quite a bit of detail on land. Here in the southwest of the US, we have an area called the Basin and Range. I don't know if any of you have had a chance to read the John McPhee book, Basin and Range, but there's many parallel, very systematic ranges, valleys throughout hundreds of miles of the southwest US. Here we have a lot of geologic mapping people can take as long as they want, spend their whole summers geologic mapping. They can use seismic exploration tools to look at the deep structure, and a lot of mapping has been done. And it's this type of structure that's been documented on shore, and we're starting to see a lot of corollaries in how this system works in the ocean. So here's just an example from Brian Wernicke at Caltech, who's worked a lot in the Basin and Range. And it's the same kind of cartoon as I showed you a minute ago, where you initially have a block where you have an upper crust and a lower crust, and then the lowest, in this case the mantle layer, is white. You start off with a regular rectangular block, you pull it apart, and in this case, it eventually pulls apart as much as 76 kilometers, so many tens of miles. What happens is you develop an initial fault. As you continue to pull it apart, here's the domino blocks being kind of rotated and laid over on their side, and you're starting to expose what was a lower crustal layer. And as the system proceeds, you get to the point that you have many of these domino blocks off to one side, and eventually you expose even the mantle layer, what was previously a mantle layer. And so it's this part of the structural system that we think we're seeing at the Mid-Atlantic Ridge and the Atlantis Transform, and that we're going to be trying to investigate. So we're going to be looking, you can see here, you have one type of what should be upper crustal rock next to what should be lower crustal or mantle rock. So we're going to be looking for evidence of that. And in fact, we have found it. And again, I'm trying to show you a side of doing oceanography and doing geology that I think doesn't make it into the general public as often. But because here at the aquarium, here at Scripps, one of the things we try to do is talk about how the solid earth interacts with the fluid earth and in fact the biosphere. I'm going to go ahead and give you a little bit of solid earth, but it won't be too much, and we will be moving on through the hydrothermal system. And I will be finishing up with some video of the new Alvin data that we collected, and you'll get a chance to see the Lost City hydrothermal system. Okay, what's going on though, as we have these plates pulling apart and we have transform offsets, you know, when you pull a knife through honey, for example, you have to exert a little bit of pressure. Well, basically that means there's stresses within the honey because of the fact that it's not just water, it has some strength to it. Well, the same type of thing goes on in the Earth's mantle. You have the rigid plates pulling apart, that's bringing material from the deep fluid viscous mantle up, and there's stresses in that fluid. And those stresses actually act in response onto the plate, and some of those stresses are responsible for building the topography. So it becomes all of an interrelated system. The deeper flow affects the topography of the seafloor, which then affects the faulting, which then affects the hydrothermal systems. Okay, so we have viscous stresses in the mantle due to the flow. The plates, an important thing in these areas is that the plates are not at constant thickness. I've been showing you blocks of rectangular constant thickness plates, but in fact at the spreading center the plates are new. They're still warm when they first come up. It takes them a while to cool. It's only when they've moved off axis that they've thickened to their full thickness. And so at a ridge transform intersection there's juxtapositions of different thicknesses of plates, and that becomes key. Normally the mantle upwells to supply the spreading plates. But what happens is that the transform offset, the material can't upwell because you've got a vertical edge, and I'll show you a cartoon in a moment. And so that means material has to move along the axis from the mantle, and then you have these stresses that I've talked about. Okay, so let's look at a cartoon. This is now based on a cartoon from a computer model that I've run, and what we're doing is we're looking through the plates, and we're looking at the shape of the bottom of the plate. And so I'm just trying to highlight the fact that you have, here's one ridge spreading center, you have a transform offset, here's another spreading center, a transform offset, and a third spreading center. And what we're seeing is how the plates are thin at the axis and how they deepen off axis with age. And so what I want to illustrate with this cartoon is that the transforms, there's a vertical wall. And it's this vertical wall that ends up inhibiting the rate that material upwells. Normally away from the transforms you have upwelling that's fastest at the spreading center, and it kind of rolls over to follow the plates as you move off axis. But that upwelling has to decrease at that vertical wall, so material has to come from the center of the spreading center and move towards the transform. And you end up with a circulation. It's a very slow circulation, but it's the same type of thing as an eddy in a stream that you've all seen. And that circulation develops stresses that are partly vertical and contribute to the topography. Okay, this is just to illustrate those stresses, and then we'll be moving on to something that's maybe a little less abstract, not so much the computer modeling side of things. This over here on the side is the same cartoon I just showed you, and what we're doing now up here is looking at the plate itself. This block actually sits right here and down off to the right side. So here's the spreading axis, here's the plate thickening with age. And these panels here are several different slices through the plate. The bottom panel is right in the middle of the spreading segment, away from the transform, and then as you move up in these panels you're getting closer and closer to the transform. Here's the base of the plate, shown along here. And the colors within the plate just indicate the vertical stresses that are acting, that the plate is feeling due to this flow in the mantle. So away from the transform, you see the red colors, which indicate a suction down. So it's pulling down at the rift axis, or the rift valley. But you can see that it's rather symmetric. We're just seeing one side of the plate. The other side would look exactly like this. As we start to move towards within about 15 kilometers of the transform, we're starting to feel, in fact, a little bit of up push here. As we get closer, we feel a stronger up push and a little bit of down pull off axis. And as we're within 5 to 10 kilometers of the transform, there's in fact a stronger push up and a stronger pull down to the side. So it's this kind of thing that you need to generate that tie relief. But this prediction from these flow models says, well, you ought to feel these stresses all the time. But in fact, these core complexes, oceanic core complexes, only develop now and then. So the key comes into other properties, the faulting, the distribution of faults that happen within the plate. And those change throughout time. And when we get to a situation that the combination of magma supply that relieves stresses and the particulars of the faults that happen to be forming, when they get to the right situation, then we get to the episode that we form the core complex. Okay, so here we are. This is the main study area, and we're going to be looking at the specifics now from now on. Here's the Mid-Atlantic deep spreading median valley. Here's the transform fault, and you can see here a little pressure ridge. This is actually really typical of the types of San Andreas type faults. If you go up Central California, you can see these types of pressure ridges as well, really quite well displayed. So here's the shallowest southern part of the region. Here's what we call the dome of the core, and this area here is what we call the hanging wall. The interpretation is that this wall, which is, I'll show you, upper crustal material, used to sit up top here. Or in fact, you could think of it the other way around, that the core used to sit down under here. And it's been peeled off from underneath. And in fact, these corrugations that you can see are grooves on the fault itself. There's grooves here on the top of the core. And in fact, if you could look at the underside of the hanging wall, we would expect to see them there. They mark the slip motion between the two blocks. Here's evidence that that hanging wall is in fact upper crustal material. We expect to see basaltic type volcanism. Okay, what I'm showing here is sonar data. It takes a minute to get used to what it looks like. The ship is actually traveling. We're towing a vehicle at about 500 meters off the seafloor here. It's a sonar vehicle. It sends out a swath of sound. That sound, if it hits, for example, a wall, the sound comes bouncing back to the instrument, and the instrument records it. And it continuously records as it moves along. So this is about 3 kilometers from where the vehicle is out to the extent of the coverage. So here the vehicle is moving up along this path. In this case, from here, the sound goes off to the side. Here you can see a white area. That indicates a strong reflected return. And so we interpret this as a small fault scarp right there. In this area, for example, not much energy comes back. And we think this is probably a little bit of sediment on top. But the area, the reason for showing this slide, is this area here. This kind of hummocky, rounded stuff is very typical of volcanic morphology. And in fact, it takes a minute to see it, but if you look right here, here's a round top of a specific seamount. You don't get much reflected energy off the flat top, but you do get a lot of reflected energy off the steep sides. And so that's a very classic volcanic structure. Other ones are shown here. So we have good evidence of that kind of morphology on that side block. I'll show you later, we also have rock samples that are basaltic. Looking on top of the dome, the faulted surface that we interpret, here's another sonogram where the ship is traveling up the center, and we see where the corrugations were at a finer scale. We see these striations in the acoustic signature. This is a really typical thing you can document on land where at all scales you have corrugated fault surfaces, and the closer you look, it's kind of a fractal type of distribution. The closer you look, you get small scale offsets. Every time you step down in scale, you see this. These are directly parallel to the corrugations that we observe, and in fact, it turns out that both the corrugations and these striations are parallel to the spreading direction. So this gives us confidence that we're seeing, in fact, what's likely to be a faulting process. This now is data from the vehicle towed at 500 meters. We saw similar striations at an even smaller scale when we towed the vehicle at 100 meters off the seafloor. So again, as we step down, we continue to see this. Gravity data. Jeff mentioned that's one of the pieces of data that I work with, and it's one of the ways that we can distinguish between rock types in a remote way. In this case, I'm showing data with a map view, and this is now the same area. I don't know if you can make out the white contours on here are the topographic contours. Here's the median valley here, so you can see the deep closed contour, that ridge transform intersection basin. And here's the top, shallowest part of the feature. So we're looking at a map of the gravity field that we obtained with a sea surface, with a ship on the surface carrying a gravimeter, and we drove many track lines back and forth here. And I've compiled the data and made a map so it's all continuous. What shows up in this map is that you have things of varying density. Colors at this end of the scale are higher density. Colors at this end of the scale are lower density. So what we see in the southern and eastern part of this topographic feature, we have indications of higher density material. We would expect that the mantle rocks, or perhaps the lower crustal rocks, are higher density than the basaltic rocks. And so we're starting to see, oh yes, sure enough, this isn't all the same material, it's not all the same structure. If we look at a profile across this map, we get the black line here. That's just a repeat of the exact same data, and you can see the high values of gravity. The pull of gravity is stronger, higher densities. What I've done down here is take the topographic profile of the seafloor and try and say, what sort of distribution of densities would I have to predict? And that's the green line is the prediction of the gravity field. And what I've done here is determined that you can have wedges of high density material. Here the pink blocks are higher density material. And they're juxtaposed to domino tilted lower density blocks of material. And if you remember back to the cartoon of the basin and range, these systems of blocks where this would be interpreted to be a fault along here are the type of things that we've seen in the continental core complexes. So it's a consistency check. It's not a proof, but it is consistent that this type of structure could produce this type of gravity signal. So we're encouraged. We're still moving along this sort of hypothesis test of does this structure hold up. Okay, so we have gravity evidence. What I'm going to move to now, and what I'll be showing for the rest of the talk, is the new data that we collected on the cruise. It was a 39-day cruise in November and December of last year. And this is now the 4th or 5th cruise to this area. It takes a long time. Just to give you a feel of all the data I've been showing you so far, the shipboard data, that was already 3 cruises worth of data, and each of those cruises is on the order of a month long. Now we're going back again, and in fact what I'll end with is our interest to go back at least another 2 or 3 times. This is the sort of commitment you need to make to get a handle on these problems. And of course every time you go back you find some answers, and inevitably you find new questions. It's, I guess, one of the things that keeps us involved in this process, but there's times where you kind of would love to have just the answer, but that's how science is, and that's part of the excitement of it. Okay, so here we are. We're the same coverage of the Massif. The blue lines are tracks of the deeply towed side-scan sonar system I referred to. The green tracks are where we towed a photo imaging system very close to the seafloor, so we actually got video coverage of what the rocks look like. The white stars that you can probably just make out here are where we picked up rock samples with Alvin. So basically they show where we took the Alvin submersible. One thing I wanted to point out here is the pink dots. Here, there's actually 12 of them on here. Those are navigational instruments. One of the things that we have to worry about when we do this kind of work is where are we? Where are the structures that we've seen? Now the ship, of course, we have GPS contact, and we have continuous, actually pretty good positioning with GPS. But these instruments in the water column can't have GPS receivers. So they need these type of transponders that ping. They send off a sound signal into the ocean, and the travel time between the instruments and this whole network of transponders allows us to triangulate and calculate what the position was. And so, in fact, what I'll be showing, I'll show you an example of what that pinging sounds like when I show the Alvin video. You can hear the pings going off in the background. And it's just part of what goes on when you work within the column, the water column, and on the seafloor. Here's just an overview of the Alvin. The ship is the RV Atlantis, run by Woods Hole Oceanographic. It's something like 280 meters in length. You can see the large A-frame on the fantail, and here's the submersible Alvin just about to be launched in this case. If you stand on the fantail and you look forward, you can see the hangar where Alvin stays in transit while we're basically prepping it to go over or unloading the samples and stuff as we've come back. 3 people can fit in the submersible. It's a pretty small sphere. People my size actually are not too uncomfortable. People that are 6 foot tall are somewhat folded up, and they're tired of being in there by the end of the 6-hour dive day. You dive at about 8 o'clock in the morning. You use battery power to maneuver around. So depending on what the activities are, you have either from 5 to 6 on up to as much as at most 6.5, 7 hours on bottom time. And then you come back to the surface, the batteries are recharged. And in fact, the way we ran the cruise, it was a rather busy cruise. We had the daytime Alvin activities, and then at night, we put the Argo photo imaging system overboard, and we spent the whole night. So you're operating 24 hours a day. Now we have shifts of people, almost nobody. I mean, the chief scientists and the co-investigators tend to stay up close to all day, but we do try and get some sleep some of the time. But most of the science crew is working on watches. Yeah?
What depth does the Alvin go to?
It can go as deep as 4,500 meters. In this particular expedition, we ranged from about 700 meters to, I guess I was on the deepest depth at around 2,900 meters. So in fact, the deeper parts of our study area, though it does get down to 5,000 meters, most of that is rubble, stuff that's been failed away, landslides and stuff. So we stayed in the areas where when you have material that landslides away, then you expose new rock, and that's where you can get the most information. So that's where we tried to work. Okay, so here's a launch of the Alvin going off there. Now some pictures before I show you the video, just to give you an idea. Here now are your inside Alvin. There's cameras mounted on the outside, and these are shots taken from Alvin on the sea floor. Here's the gravimeter. This is the gravimeter developed by Mark Zumberg, Glenn Sasagawa, and his group at RGPP. This was the first time it was used in a deep water environment. And in fact, it was very impressive. A lot of times with marine instrumentation, there's significant development, trial and error, things that you think work theoretically, but then when you put them into practice in the water, it's difficult. This actually worked excellently for a first-time use instrument. It was really quite impressive. The milk crates, it looks like kind of a jumble, kind of junky. That's just a very durable way to store rock samples. And here I show the robotic arm, and these fingers, the hand opens and closes, and there's a rock sample in the hand, and this rock sample then gets put in one of the milk crates, and we can bring it back up to the surface. Here's an example of how we map faults. You can see here kind of linear features juxtaposed to a more massive piece of the rock, and in fact more massive over here. This is a small fault, and so this is one of the ways we do geologic mapping down there. Remember, of course, there isn't naturally any light, so part of what's going on is that we're using battery power to light up this whole environment. You know, we joke around, people that are geologists say, oh, you know, how can you work in the oceans? Well, it's kind of like working at night on land with a flashlight. You know, you really have a tiny field of view, but you do have a view, and that's the key thing. You know, it's the information that we can obtain. Here's, very quickly, a look at the distribution of rock samples that we obtained. Again, this is the same map area that I'm showing. We have the Rift Valley coming down here, the Transfort Fault is just here, and here's the shallowest part of the Massif. And you can see the red basalts they're found from outcrop only in the hanging wall block. There's some basalt rubble up on top of the dome. There's some serpentinite rubble on top of the dome. Down in the core, what we call the core of the Massif, which we can access on that south wall, it's almost all gabbro and peridotite, so lower crustal, upper mantle type rocks. The one basalt sample that we found here is a small dike that runs through. So this is good confirmation of the juxtapositions of basalt, upper crustal rocks against lower crustal rocks. Okay. Now, Argo, and I'm going to move into, I think, what was the most exciting part of our cruise, and maybe what got some of you here, is how we discovered the hydrothermal system. We did go out to sea expecting to find interaction between seawater and the lower crustal rock. That was why Debbie was out there with us. We didn't expect to find such an active hydrothermal system. With this photo imaging system, here you can see the aluminum frame inside our computers that are storing data and transmitting it up a fiber optic cable. Here's cameras that we use. There's continuous real-time video that we monitor on the ship while we're towing the vehicle down very close to the seafloor, 8 to 10 meters from the seafloor. And we also have a digital still camera, which is a really technologically impressive camera that has very detailed, high-resolution cameras at these low light levels. So here's some examples of very kind of the rounded basalt, very typical basalt here. This is a couple meters across. Here's just an example of one of the things that was frustrating to us. There's sediment on top. It's not thick sediment, it's only about a meter or two, but for us with the submersible or with some of our sampling tools, we couldn't get through that to work on the top. Now we did get a lot of work done on the side, but one of the reasons that we're pushing hard to have an ocean drilling program back to this area is because we can't do the geologic mapping up on top. We really need to be able to punch through that sediment layer. Okay, it was with the Argo one of our night projects. We were about 4 days from the end of the cruise when we discovered the Lost City hydrothermal system. We've been working, doing detailed photo imaging of a steep scarp up on top of the southern wall of the massif. We'd spent already 4 days doing this type of work. Then one night, we were looking at the radar system. Argo has, or a sonar system. Argo has a sonar system similar to what a fishing boat might carry, where the vehicle is here and it sends off radial energy and looks for returns from some structure, some obstruction. So what you're seeing here is a return from, in fact, a small ridge. The scale here, each of these lines is about 10 meters. Here's a ridge that's only about 12 meters away from the vehicle. Here's a ridge that's 20, 30 meters away. You can see that the ridges continue for, some tens of meters themselves. But what's interesting are these shadows back here. These, in fact, indicate the pillars of the hydrothermal vents. And it was some of our first indication that there was some interesting structure here. The jitteriness on this screen is because it's just a camera shot of, there's some motion of the ship. Here's one of the spires that sits atop these ridges. There, as I can hear your response, this is how we were feeling. And this is one that's not active. There's no longer fluid venting through here. But we had the same reaction. All of us are familiar with hydrothermal fields, as you are, on active spreading centers. Here we are somewhat off the axis. There's no evidence of recent volcanic activity, and yet we were seeing what at least had been in the past a hydrothermal vent. So of course our interest was perked right away, and we thought, oh, this is cool. So we're going along and we're towing this vehicle. I guess one thing I want to point out here is the operations. This now is over 10 meters high. Now remember, we're on a ship. We've got a cable, a fiber optic cable, to which that instrument, we're towing this instrument along. And basically the ship is having to pull the vehicle around this system. And it really is a tribute to the guys, the Woods Hole guys that run this system, that we had no operational problems operating in this kind of environment with a towed vehicle that close to the seafloor. It's a challenge, and they did an excellent job. Here's a cartoon, before we get into the video of the system, here's a cartoon of, here's some vent structures. They fall apart, bits of them build up a mound around the structures. Fluid, as we'll see, there's several active chimneys in this system, and the fluid will often vent out here. Sometimes the chimneys will crack and vented fluid will come out the side and a flange will build up. And you've probably seen those from the Wanda Fuca. They're actually quite beautiful, and we'll show you video of that. But here, just to try and make one final connection between the deeper structure, here's the peridotite rock that's been uplifted. I mean, we know there's peridotite in that upper 100 meters of the south wall. Here's a fault through it that allows the seawater to go through and circulate, interact chemically with the peridotite. And that's the key here. That's where the heat is coming from, it turns out. It's not volcanically driven heat. When seawater interacts with peridotite, the mantle composition rocks, that's what we call an exothermic reaction. Heat is given off. The mineral structure changes and heat is given off. And so in fact it's that heat that drives this hydrothermal system. What's impressive is that we measured temperatures on the order of 75 degrees centigrade, 160 degrees Fahrenheit. Those are pretty high temperatures. Now, they almost certainly with this kind of a driving system doesn't get hotter than that. The black smokers are up around 300 degrees C, so they're quite a bit, they're a rather different system. But still, this is a large massif of serpentinite, of peridotite. There's many fractures in it. There's the opportunity to have a lot of this reaction going on. And the height of these chimneys, some of them reach 60 meters high. That means it's been sustained for a long period of time. The precipitation of the chimneys, you have the water circulates through the mantle rocks, picks up minerals and chemicals along the way. It's hot enough that it can hold those minerals. Once it comes out to the seafloor, the seawater's cool, and the water can't hold those minerals. They have to precipitate out. And so that's how you begin to form the chimney. Once you have the chimney there, that then further channels the flow, and it kind of becomes a self-propagating system, at least for a period of time. Okay, before I move to the video, just one final thing. Here now is just a blow up of this area, the mound, the circulation of the seawater. Here's one of these flanges, and the scale of it is on the order of 1 meter across, and often they have some pretty interesting detailed structures built up on top. Blowing this up, we actually brought back a sample from one of these features. This now is 10 centimeters across. And if then you magnify this, here now we're at 25 micrometers, This shows the structure of the brucite mineral. It's a manganese hydroxide. These are not sulfide systems. They're completely different than the other hydrothermal systems. That becomes key. As we look at the figures, you won't see lots of interesting tube worms and clams. The chemistry, the biology is completely different because it's not an iron sulfide-based system. One of the things that's got us quite intrigued here, and I'm not a biologist, but Debbie Kelly and her co-workers up at University of Washington, other workers here at Scripps, with this fairly low temperature system, with the likelihood that you don't have to have active volcanism nearby to have this kind of a system, we're very much looking towards what are the likelihood, the biology that we've looked at here when we've done the analysis, it's very primeval. And one of the real interesting things here is, do we have a corollary with some of the type of environments of early Earth and the beginnings of life? So it's very exciting from that point of view. We're very early on in that part of the study. We're trying to get back to this area to get more samples, but it's a very, very strong pull, I guess, to get back and continue working in this area. Okay, let's move on and go towards the video. This, I think, visually you'll find quite interesting. And then I'll be finishing up. Okay. This now is video that we obtained during the single dive. Because we discovered this towards the end of the cruise, we only had time to have one dive down to the area. The field of view here is a few meters. It varies as you move in and out from the structures.
Delicate little fingers sometimes.
The voice you hear in the background are Jeff Carson and Debbie Kelly, who dove, and then there's an Alvin pilot with them.
Over the slope here, it's clearly very delicate stuff preserved here. The older material has a slightly browner.
You don't see a lot of tube worms, but what we will see in these next few frames is the sort of flowing filamentous bacteria, and that is one of the visual parts of life. Yeah.
Is there much of a current at that depth?
There is, yes, and in fact, you're right. Think of in a mountain with the wind. We're right at the top of a mountain, and in fact, it's a few knots, or a knot or two. It varies with the tide.
Oh yeah. There's a nice view.
The depth down here, yes, it is meters, so 730 meters, which you see down at the bottom there. Here we are. You can see the flowing bacteria. The shimmeriness, it's not out of focus. That's because of the difference in the water properties. We'll see some of the shimmering now, and then other shots won't have so much shimmering. Okay, this is now taking the temperature probe and trying to measure what the water temperature is. So you can see they put it right into the structure to measure these high temperatures.
When did the 3 chip just a tad?
There, you can see small things flitting through here. We're actually not certain what those are. It's possible they're shrimps. I mean, one of the things we would expect in this kind of system is small shrimps. We don't yet know if they're there or not. The time of day is up at the top, the dive number, heading of the vehicle. Makes the photo a little messier, but it's critical when you're down there. You need to keep track of where you are, what's going on. Now here we're comparing, see how light the one side of the structure is there, and as we're looking towards the background, it's darker. That's an indication of the activity. It turns out it's only the actively venting sites that are the white, the bright white. That's part of the organic material associated with the current activity. As you move away, it goes to more kind of a gunite or cement type of color in the background. The noise you hear, hopefully it's not too obnoxious, that's the running of the propellers, the electrically driven propellers. And if you listen carefully, you'll hear some pings in the background. Those are the navigational stuff. And it's also, we're talking to the ship.
70% of that is leaching water around this entire.
It's, in this case, only very close. That's one of the, operationally, you always worry a little bit about that, but from working in the systems that are the higher temperatures, 300 degrees temperatures, it can take that temperature, and it turns out it's so localized that it's really only the probes are sticking in that are feeling that high of temperature. All you have to do is move away about a meter, and you're fine. Here you can see some of the fine pinnacles sticking up the structure.
How tall is this?
This one, I'm not sure about this one. The one that we'll end up on is 60 meters. Here's a case where an older one, we just missed it, but we'll see some more. Once the venting activity stops, corals begin to grow in these things. It's shallow enough that corals will develop. You can see some of those small bits of corals here. But it's a lot easier with the video to kind of get a sense of what these structures are. You can't, with a still frame, it's too hard to capture the whole thing. And this, I think, gives you the feel of what it's like. I mean, this is real time. This is the rate at which the submersible is moving around, viewing. We're here having mainly the pilot's view. Remember, that was a small porthole. The pilot, of course, takes the best view because he has to control the operations. He has to know the most of what's going on. The two scientists look out to the side. But part of what's going on with the talking is that they're telling each other what they're seeing because they can't see, you can't look around. You've got that one little porthole view. So here we are coming down. And now we're looking at a place, this is a small part of a flange. And in fact, it's a place where they broke off part of the flange to bring back and to try and analyze the chemistry and the biology. There's some very tiny snails that are within the structure. We weren't sure what they were at first. They even almost looked like fleas, but in fact, they're very tiny snails. So even though you don't get in with this kind of a view, you don't get to see a lot of the life. At a microscopic scale, there's microbiological organisms here, archaea, eubacteria. So there's definitely quite a bit of life here. In fact, within the flanges, it's very dense microbial communities. It's in this case, they were within the. No, we didn't pressurize. We didn't have, because we didn't expect this to be a big part of what we were doing, we didn't worry about the pressure. So in fact, the snails probably didn't survive the transit up. The biology, some of them did. We, in fact, as soon as we got them on board, we kept them frozen and transported them back as you need to do. And in fact, some of those were cultured and were shown to, in fact, continue to grow later on. But it's that whole suite of in situ characterization of the biology and the temperature that needs to go on, and Debbie and Jeff will probably go back to do that. Yes, yeah, when you see the sort of shimmeriness off to one side, yeah, that's the hot water coming out. In this case, we couldn't freeze them to bring them up. We don't have that kind of equipment. As soon as they came on board, we put them directly we sealed them up, made sure there was no atmosphere in the system, withdrew any atmosphere that might have gotten into the sealed container, and then put it in a freezer. And then we transport it by air in a freezer back to the lab. Yeah, you really have to take a lot of care when you're dealing with this sort of system. Those of you that have been in caves will see these are reminiscent of the stalagmites and stalactites. It forms, the water flow is from the inside out rather than dripping down, but the mineral precipitation and stuff is similar. You'll hear these guys chuckle in a minute. One of the things that went on throughout our Argo tows and during the Alvin dive is there was a big, about 4-foot grouper that was swimming around. He was sort of curious. We don't actually have a picture of it in this part of the video, but here's now a good example of one of the flanges. And what they're doing is coming down to look. Because the hot water does come out of these flanges and it cools underneath them, the difference in the water properties ends up resulting in kind of a mirror-type character of where the two water properties meet, and you get a reflection off the bottom. You may have seen some pictures like that from the Wanda Fukin. It's really quite spectacular. But it's also a nice indication of the strength of the difference in the properties of the water. So you get some information just from the visuals, even if you haven't taken a sample. Okay, and this is just about all I have. But just to summarize, just let me remind you that here we're working in an area of extreme topography on the seafloor. This results when the forces associated with plate rifting produce asymmetric low-angle faults and resulting vertical stresses associated with mantle flow and the flexure in the plate. In these type of areas where you have these large core complexes, the transform offsets seem to play a key role in the development of these kind of geologic structures. To understand how this system forms, what the structure is, you really have to use a suite of shipboard tools. You need the shipboard, kind of the large scale view of things, so you can have the context so that we can understand that these things are episodic, they don't happen all the time. But we need the very detailed stuff to get down and really measure the water chemistry, map the faults, and in fact sample the biology. This takes many cruises, months, repeated visits to a site, and each time you go back you understand, okay, this is how I need to focus the next expedition. And then finally, the Lost City hydrothermal field is the first known system like this along a spreading center. We're not right in the axis, but we're just off axis. And the heat is derived dominantly from the chemical alteration of the rocks. It's not a magmatically driven hydrothermal field. The temperatures we're seeing on the order of 75 degrees C. The chemistry and the biology are distinct from other hydrothermal systems near spreading axes. And there's this very interesting hook that this type of low temperature, slow reaction may well be representative of some of the early Earth environments. So we have an opportunity to try and pursue those kind of questions further.